Welcome. Another idea that comes up in Chapter 8 is this idea of resonance. And it occurs when a molecule has at least one double bond and one single bond between two of the same elements, which means more than one Lewis structure is possible because the double bond could be in either place and then the single bond could be in either place. And the reality is the electrons flow back and forth between these two places, so the pi bond or the second bond moves back and forth. So the molecule is really like it has two 1.5 bonds. Neither one is really a single bond and neither one is really a double bond. Instead, they're kind of like 1.5 bonds. So that's where the word resonance or resonate comes from, because resonate is like vibrate or to move around in an area. So let's look at my example here, SeO3. So selenium trioxide has got 6 electrons from the selenium. Oxygen, being in the same family, also has 6 each. So you have 24 electrons to get all 4 atoms stable. So I'm going to put Se in the center, attach my 3 oxygen with single bonds, fill in my lone pair. So each oxygen still needs 6 more electrons. And selenium also needs a lone pair. So now when I count up, each oxygen has 2, 4, 6, 8. So 10, 12, 14, 16, 18, 20, 22, 24. Plus the lone pair on selenium, I've used 26 electrons. So that lets me know I need to share another pair. So I'm going to go ahead and share a double bond between this selenium and oxygen, which means selenium no longer needs that lone pair and oxygen only needs the 2 lone pair. And now when I count up, I have 24 electrons. Now the question is, why did the double bond go between this oxygen and selenium? Why didn't it go with one of the other oxygen? And the answer is it could have gone to any of them. So this would be more correct if I went ahead and drew the other possible structures. This could just as easily be Se double bonded to this oxygen and single bonded to the other 2. And I still need to draw in my lone pair. Or it could also be the third and final version where Se is double bonded to this oxygen and single bonded to the other 2 with the lone pairs indicated. So drawing resonance structure means drawing all the possible places where that double bond can resonate or rotate among. So here's another example. It says draw the Lewis structure for S2O3. And then I've given you a hint here. It says the double bond will occur in the center of the molecule if possible. So really, this would be better classified as a non-example, because when we look at this, I have sulfur. Sulfur each have 6 electrons. Oxygen also has 6. So I've got 30 electrons here. So when I draw this, my 2 sulfur atoms go in the center. I have 3 oxygen to attach. So I'm going to attach them like so, and then I'm going to figure out what I need for lone pairs. So this oxygen still needs 6. This sulfur still needs 4. This sulfur only needs 1 lone pair or 2 electrons. These oxygen each need 6 or 3 pair. And now when I count up, I've got 2, 4, 6, 8 around the first oxygen, 10, 12, 14, 16 around the next oxygen, 18 on the sulfur, 20 between the sulfur, 22, 24 on my second sulfur, 26, 28, 30, and 32 electrons. So I used a total of 32 electrons to get all of those atoms stable. So again, that lets me know I need a double bond. Well, in this case, the double bond is going to form between the 2 sulfur rather than with one of the oxygen. Okay, so this would not have resonance because the double bond is not going to rotate from between 2 sulfur atoms to between a sulfur and an oxygen atom. The resonance has to be between like atoms, and I only have the 2 sulfur atoms. So kind of the rule with atoms is or molecules is they're going to do whatever they can to keep things balanced around the center of the molecule. So that's why I can assume the double bond would form between those 2 sulfur in the middle. So that's a non-example of a double bond without resonance between it. So here I'd encourage you to pause and try this one. Draw all the possible Lewis structures for CO2. So if you count your electrons, you have 4 for the carbon, You have 2 for each oxygen. I've got 16 total. So when you draw this, if you start with a single bond with each oxygen, filling in my lone pair, I have 6 on each oxygen and 4 lone pair, or 4 electrons, 2 lone pair on the carbon. And when I count up, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used 20 electrons. So I'm short 4 electrons, which lets me know I need a double bond on each side here, which means I can lose a lone pair from oxygen and the carbon and from the other oxygen and carbon. So since they're both double bonds, there is no resonance. This is the only possible structure, is a double bond on each side. And then here's one more for you to try. See if you can draw CO3 with a -2 charge. So look at this. I've got 4 electrons from the carbon, 6 from each oxygen, and then they've picked up 2 from some metal. So I've got a total of 3 times 6 is 18, 20, 24 electrons. So when I draw in CO3, I'm going to need 2, 4, 6 on that oxygen, 2, 4, 6 on each oxygen, plus the carbon needs a lone pair. So now when I count up, I have 8 around each oxygen, so 8, 16, 24, and then the other lone pair on the carbon means I've used 26. So I am going to need a double bond here, which means I save a lone pair from each atom involved. And now I do have resonance. So my other possible structures would be to have the double bond in this position, or to have the double bond rotate or resonate over to this position. And remember, it's not considered a complete structure without accounting for all the electrons, so make sure you draw in the appropriate lone pair so I can see that each molecule has the 24 electrons.